rate constant is then simplified into just these two terms, log KH plus log H plus, all right, and then all everybody know that negative log concentration of H3O plus is actually pH. Okay. Okay, so then from there we can just have the term pH there in the equation. So what happens if it is not H plus, which is the main catalyst in the reaction, but OH? So we've got another different equation, as you can see from here. We have also what we call as POH, but POH is negative log OH. But we not normally use POH. We only use pH because pH we know pH plus POH is pKW. So meaning that if we want to show the acid level, it is of course pKW minus POH. So we will see that the value will be around like 9, 7 over to 14, for example. These are the value for pH when the concentration of OH, or the concentration of hydronium ion or hydronium ion is higher than the concentration of H plus. All right, so I think those are the things that you already know. If under any condition that KOH, that KO is larger than KH plus, and so that there where you will have the log K is equal to log K naught, and slope will be 0. And that is where the reaction reach the minimum rate at that stage, where if you have this situation, okay. Let me just okay. 100% okay. Okay, and then specific base catalysis, just to summarize, and then the mechanism, and then I've shown you this one. This is the mechanism. We have seen this in case of acid-base catalysis. You can see that if you have pH plus, if we have pH plus as the acid here, right? So, and the substrate, or you can say the sample, or the reactant that where we want to catalyze the reaction. So we want S to become P at the end of the reaction, right? So S to become P. So this is the product. Okay. So this is the reaction that the mechanism that is proposed for the proteolytic and prototropic reaction. So you should be able also to identify what is proteolytic, what is prototropic. Okay, so when the prototropic is when proton is transferred to the solvent, as you can see from here. So if solvent is water in this case, of course, In case of acid-base catalysis, all the time we are using water. But the proton can also be transferred to the solid, or in this case written as B, for example. So the solid itself is actually the if you refer to this reaction step, you can see that BH plus plus S, then the B is actually the solid added into the solution. Okay, so and the other thing that you should also identify is what is intermediate in this case, because it is important to identify the intermediate so that from there we are able to derive what is the rate of the reaction based on the mechanism given, right? So, and of course, we know that the rate of the formation of the intermediate, according to the steady state approach, should be 0, right? So that one is everybody know. So in this case, of course, we know that SH plus is the intermediate. So meaning that the rate of the formation of SH plus should be 0. And from there, you should be able to see which one involved SH plus. So what is the rate of formation of SH plus? Okay, you can see that the first reaction involves SH plus, and the first reaction is the formation of SH plus. So meaning that if you are to write that, you should write as K1 equal K1 BH plus S. Okay. So the second reaction, which is the reverse of the first step, though, the reverse of the first step is the second reaction. You can see is the consumption of SH plus, so that will be negative, and the rate constant is K2, and the reactant involved for the reverse reaction is BSH plus. Okay, and SH plus also involved in the third and fourth reaction. But anyway, we are looking at one, for example, if we are considering protolytic reaction, then only number 3. So and then so we have to. This is also the consumption of the SH plus. Then it should be. I'm running out of space. K3SH plus, and we don't normally put water because the concentration is the water is considered as concentration 1, so only K3SH plus. And then from there, since the reaction is dP dt, the rate of reaction is you can see the rate of reaction which is the reaction which involve the product. So that will be K3 SH plus, and from this, you know, this is 0, this is 0, right? So from here, you should be able to replace HS plus into this equation, and what you will get at last is this equation. Okay, so then also that will depend on if K3 is larger than K2B, then it is can I erase this? So this is from the previous one. Couldn't erase, because this has been fixed there. Because in the last lecture I was using PowerPoint, and I was written on PowerPoint. But now I'm using notes, and I have saved this file in PDF. So then it's already fixed there. I cannot cancel. So, but anyway, yeah, you can see in your notes. You can see in your notes, if K3 is larger than K2B, then rate is equal to K1 times the concentration of SBH plus, right? But if the case of Arrhenius complex, this is case of Van Hoff complex, K3 is less than K2B, then V is equal to this. So meaning that you can you'll be able to see if K3 say okay, so it becomes so dp dt then is K3 K1 BH plus S K2B plus K3. Okay, so if K3 is larger than K2B, K3 is larger than K2B, meaning that you can ignore K2B and it is very small, and then your rate of reaction will be just K3 K1, and since K3 K1 you have K3 and you have K3 in the at the bottom also in the denominator, then the rate just become KBH times S. But then on another situation, let me see if I can go back. Alright, so if for example K3 is less than K2B, so meaning that you can then ignore this. So the situation is just become as just result K3 since K3 is small. Okay. I'm talking to myself. I hope you are listening and not doing anything else. Is my voice clear?
Yes.
Thank you very much.
Yes, yes.
Yes.
Okay. Okay, so since for the equilibrium BH plus, and then so okay, so there's another thing to consider is BH plus in the catalysis is also in equilibrium with B and H plus. We don't normally write like that. But anyway, that is the way we do it in this acid-base catalysis, because we all know that if you have H plus, it will always be combined with one molecule of water, so it will become hydronium ion. Okay, so that is the situation in the water. Right, but anyway, this is the simplified one. BH plus is in equilibrium with B and H plus. So then we can write, because we know what is K. K is the equilibrium constant. You have equilibrium constant K. You have Ka for acid, K B for base or so forth. These are equilibrium constant. So this is equilibrium constant for acid, and this is written as KBH plus. And so the rate is then since we have that, so we have rate is equal to then K1 K through S. Let's go back to the okay. So what you do is just replacing some term there in the previous equation. So rate is still dp dt. This is written as rate here, but don't confuse. And that is dp dt, right? So this is for what do you call it? Protolytic reaction. And then there's another one for the phototropic reaction, prototropic mechanism. Okay, so for phototropic mechanism, so you can see it is a little bit different from what you have seen for the protolytic, where you can see the reaction will involve the concentration of BH plus. Okay, instead of the concentration of H plus, right? So that's why it is classified as general acid catalysis. All right. So and then you come to this part, which is the summary of the conclusion of various mechanisms of acid-base catalysis. So how do you classify into the Arrhenius and Van Hoff intermediates? How do you classify them into acid catalysis and also base catalysis, right? Anyway, this is just repeating the base catalysis because it is quite similar to the acid catalysis. So what you've got to see is just on one acid catalysis. So for example, in this case, if it is Arrhenius intermediates, okay, this is protolytic and also prototropic, as we have seen as we have discussed earlier. Okay, so if it's Arrhenius catalysis, Arrhenius intermediate, for example, K2 is less than K1B, then it is specific H plus catalysis, right? But if K2 is less than K minus 1, it also become general acid catalysis. So you have got general acid catalysis and also specific acid catalysis. One half intermediates, if K2 is larger than K1B and K2 is larger than K1BH plus, it is general acid catalysis. And also if it is K2 larger than K minus 1, also it is general acid catalysis. Right? So the same thing is repeating here in the case of the base catalysis. So just study the table and see how can you classify a certain reaction to whether it is a general catalysis or specific catalysis, whether it is acid catalysis or base catalysis. Okay, so the next one is on the iodination of acetone. Okay, so iodination of acetone is the reaction of acetone with iodine to form iodinized acetone and also the HI or HI is the combination of H and I. You can see that as acid, hydroiodic acid, as we see, if we have hydrochloric acid, for example, right? Okay, so the mechanism given is shown, right? So where in the first reaction is the reaction of this is a catalyzed reaction. You can see the catalysis, the acid there is BH plus, right? So first step, and of course the reaction is a reversible reaction where the reaction can the intermediate that is formed in the first reaction can combine back with the conjugate base in this case B and form back the acid. Okay, so and then we have H plus. What is A? What is A? A is quite confusing here, right? Oh, this one is A. Eh? This A is this one. This one is A. Okay, so meaning that A is just the intermediate that's formed from the first reaction. Okay, so just to simplify the writing, so it is written as A. So you can also write A here, for example. Huh? You can write, for example, this is A, and then AH plus, right? So react with the solvent, okay, to form another species here, plus H3O plus, and this is E. Okay, this is E, and E react with I2 to form the product. Okay, so that's the product that we need. So it involves several steps there, right? So as you can see there, it involves 1, 2, 3, 4, 5 steps actually. Even though we only see 3 steps here because 2 steps are in equilibrium. So then you can write the rate of reaction as dp dt K3E times I2 based on the last reaction which produce the product. Okay, so but the E and A are the intermediate of the product of the reaction. So then it should be replaced with other terms that is measurable, because we not normally measure the intermediates, right? So then E, you can see if you use a steady state approach, you will get E as this and AH plus as this. Okay, remember it's at the steady state approach, meaning that we are assuming that DE, not assuming this is always the things that the way that we do, DE dt is 0, and also D, in this case, we are having DH plus dt is 0. Why is it 0? Because always in the steady state approach, what the assumption is that the concentration of intermediate will drop to a minimum level, and constant after the initiation of the reaction. So meaning that the concentration of E will always be minimum and constant. So meaning that the rate of production of E will always remain 0. Okay, so that is for intermediate. So that's why we can use what we call that as the steady state approach. Okay, so that will take few steps for you to get from here to here. Okay, so because you got to consider all the and from here to here. So because you've got to consider all the steps, for example, for E, you've got to consider all the steps that involve E. So the step that involve E is this one. This is also E, yeah? This is also E, yeah? This is E. This is E, and the step that involve A. Okay, let's just see the step of, that involve E. There are three steps that involve E. One is the forward reaction of this one. Okay. The second one is the backward reaction of this. Okay. Two. And the other one is this one, which the rate of consumption of E to form the product. So there are three steps which involve E. What about A? Okay. A. So this is A. So this is the step. Two reaction that involve A, and then we got another two reaction here which involve also A. Right, AH plus, sorry, AH plus, AH plus. So what's wrong there? Okay, AH plus. Okay. So the step that involve A is two step of the first reaction, two step of the second reaction. Okay. Right. So these are all considered when you do the relationship this part for AH in a sense of E. Alright, and then all of them into the reaction equation to replace E and also AH plus, and then you get the reaction in terms of the concentration of the species that can be measured in the reaction. Right. So you have A, you have A plus. Alright. But in this one, still you have E. So you still have E here. Right. Anyway, that is to also be simplified further. That is to simplify further to the following reaction, where if the reaction is occurring at high temperature, how you did it? So the reaction is occurring in high concentration of iodine. So what you will have, so then what you will have that this part will be very large, right? High concentration of iodine. And then that will become just K1, K2, A plus K1, K minus 1, B. Alright, so please check how can we get this high percentage. Okay, what you're going to do is to go back to the reaction and derive the equation. And then what you can get is that you will ultimately reach the rate equal to what we have shown here, which will be H plus minus B, which has the okay, so meaning that here you have got to remember this is A, this is This is AH plus, right? So this is the combination of NH plus. Still people are coming. This is already 8:51. Okay, so and then you have K, where A is acetone, of course. The reactant which start with acetone, and BH plus is the acid that catalyzes the reaction. Okay, and B is the conjugate acid of BH plus, conjugate base of BH plus. So when K2 is larger than K1B, so and then the reaction will be reduced to this, and this is then general acid catalysis, since it's only involved BH plus, and when K2 is less than K1B, far less, this is not just less, far less than K1B, then it becomes K2 is less than K1B, so meaning that K, what you have only left with K1B, when you know K2, right? So then it becomes like this, and you can then also rewrite the equation in this form, taking into consideration the situation where you know that BH plus is in equilibrium with B equilibrium, this equilibration with B, and also H plus, okay, and you can then get KBH plus equal to what? And then from there you can replace BH plus back into the equation, and so this is of course concentration of BH plus whatever BH plus over BH plus, and then you can get what is BH plus equal to what, okay, and then replace back into the equation. Okay, shown here in the blue color. Okay, that ends part 1. Okay, right. So what we're going to do is just to go back to the reaction and try to derive the and show that the rate of reaction is equal to this one. Okay, so in both steps, which one of the things that you get is this one, and then if the reaction is run at a higher concentration of I, then you can reduce the long formula into just a simple one, as shown here. Okay, so you go to show from here to here, how you can get. Alright, so let us move on then to the next part, which is on the part 2 of the of the catalyst reaction. So as you see that we are now on discussion on the homogeneous catalytic reaction, and the two things that we are discussing. The two main part that we are discussing, which is on the acid-base catalysis. The other one, which we're going to discuss later also, is on the enzymatic catalysis, enzymatic reaction. Enzyme is the catalyst. Right? So enzyme catalyst reaction, you can call that as enzyme catalyst reaction. So we have got acid or base catalyst reaction. We have got another one, enzyme catalyst reaction. But before we move on to that part, so we're going to also go to some other parts which involve the how do we evaluate the strength of acid and base and to see if this acid and base the strength of acid, how it relates to the reaction or to the rate of the catalysis. Okay, so we would normally assume that if the reaction has high acid properties, for example, so it will be strongly catalyze reaction which need the acid as the catalyst. So there are a few things that we want to see in this part. One is on the Bronsted relationship. The other one is on the Hammett acidity function, right? And of course, the last one is the part on the enzyme catalysis, which involve Michaelis-Menten equation. Okay, let's move to the first one first. Bronsted noted that the rate constant for reaction catalyzed by general acid are proportional to acidity constant. Okay, of the general acid. Okay, what is the acidity constant of a general acid? Okay, so we know what the Ka value, right? And also we know for certain weak acid, we also have the degree of dissociation of the acid, right? Degree of dissociation of the acid. Okay, so we normally relate the strength of an acid to its Ka value, right? Because the Ka value will tell you how much H plus or H3O plus that you will get in a solution or in water, for example. If you dissolve acid in water, and you will get certain amount of H3O plus, and that amount of H3O plus will depend on the Ka value and also the alpha value, or not alpha value in this case. This is a different alpha value. What alpha value I means that is that the degree of dissociation of the acid, right? So as we know that the strong acid will be fully ionized. So whatever concentration of the acid, that is the concentration of H3O plus or H plus in the solution. But for certain weak acids, for example, you have known about the acetic acid and so on. These are weak acid. So then not all the acid, for example, HA, in this case, not all HA will be ionized to H2O plus. Some will still remain as HA in the solution. Although they dissolve the solution, they still remain as HA. Okay, so with that, we know what is Ka. Okay, so that is already quite well known to you. Okay, and then the relationship to Ka, this Ka is the Ka is the rate of reaction, or the rate constant, the catalytic constant, acid catalytic constant. So we write that as Ka. Huh? So Ka will depend on Ga, alpha, and also Ka at the same time in as shown in this equation, right? So where Ga and also K and alpha are also constant, right? So okay, let us see further. Right, what's the relationship? So then we have here that the H plus is the acid that we are now looking at. We wrote that as a general acid BH plus. Okay, so it will ionize in water to form B and H3O plus. Then we can write the Ka value, and we know that Ka times Kb is Kw. So we can also write. We know that we can also write another equation instead of for the acid. This is for the base. And then since we like to use Ka rather than Kb, so we can replace Kb, Ka with we can replace we can put Ka into the equation by knowing this relation. So that's all. So this is for case of base catalyzed reaction. So and then you have acid catalyzed reaction, we have base catalyzed reaction. What are their constants? How they relate to the constant Gb, alpha, and beta, where Ga, Gb, alpha, and beta are the constant in the Bronsted relation. Okay, so this is just to remind you that we are now discussing on the base catalyzed reaction or acid catalyzed reaction, right? So consider that we are measuring the K for the following reaction, and the conversion of ketone to diol for 3 different acids. So these are the acid, and these are actually the catalysts for the reaction. Okay, so these are the catalysts for the reaction. Okay, so of course that we are talking about now is we are talking about the since acid involved in the reaction, acid involved in the reaction, so we are talking about the hydrolysis of acid, not hydrolysis of the acetone. Although in the reaction it is the acetone which involved in the reaction to form the product, okay, but the reaction will involve acid, and acid will go through the hydrolysis process and then same time catalyze the reaction. Okay, so how to evaluate the value of alpha and also beta? So if you go back to the equation, you can see this equation, right? So you put log Ka to the rate constant. So what you'll get is that this is log Ga plus alpha log Ka. Okay, so then it become a linear form of equation, and then from there, if you plot log Ka versus log Ka or pKa, remember pKa is, or you can also written like this. Okay, this is then equal to log, sorry, Okay, so this is then, okay, log GA minus alpha pKa, right? Because log Ka is negative pKa, or pKa is negative log Ka, right? So and then into the back into the graph, you can see if you plot like that, what you get is the slope of log K versus pKa, and then you get a negative slope there, and that will be alpha, and that is the constant for acid catalysis. The same way, you can also plot log K versus pKa for BH plus. In case of in another situation, and then you will get the slope as B, right? Or not B, beta, sorry, beta. The slope as beta, and that is the uh, slope for, you can see that this is positive. Log Ka versus pKa, it is a positive slope. And depend on the, you can go back to the equation and try to see what's the relationship between Kb and pKa there, and then you can see that it is pKa there will be positive in the relation, right? Because you can see that this is at the denominator. Okay, so then from there we can evaluate the value of alpha. Alpha is extent of proton transfer in the transition state. Okay, alpha equal 1, meaning that acid has completely transferred a proton to the reactant. So for case of like we have a strong acid, so we'll get the alpha equal to 1, alpha to 0, no sensitivity of the reaction rate to acid strength. So you can see from, you can go back to the equation there. So if, for example, you replace alpha to with K1, alpha with 0, for example. If alpha is 0, if alpha is 1, if alpha is between 0 to 1, right? So what happened to the Ka value? Okay, so the Ka value will depend on the value of alpha. For example, if alpha is 0, then Ka times 0, then Ka will only be Ga. The small Ka, the small Ka will only be Ga in case of alpha 0. If 1, then it will be only Ga Ka, right? So you can do that and so on, right? So the same way for the beta, right? So you can also evaluate that. Okay, so try to answer these questions. I don't want to go through this all. These are already answered in as I shown you. But anyway, just go on with the 1, 2, 3, 4, 5. See if you can understand what has been discussed by trying to answer all these questions. Okay, acidity function. Okay, so pH is the most popular indicator of acidity. So if it is strong acid, the pH will be low. If it is strong in base, pH will be high. If it is strong, not so strong acid, you know that the pH will be around like 5, 4, and so on, right? So that will also depend on the concentration of H plus. Okay. For protonation of base B, BH plus plus H2O protonated base, BH plus. If you consider this as a general form of acid, and then it will also be in the equilibrium with H2O plus. So then the Ka value we can write as shown, and then we can transfer that into a different form, into the log form, as shown. Okay, so that is quite straightforward for this acidity function. So what we have seen here is the alpha beta value, how it relates to the strength of acid and base, and then how it affect the value of Ka, which is the rate constant for the reaction. Okay, how the rate constant for reaction relate to the value of alpha and also Ka, and also we have seen that here is the Ka value, how the Ka value relates to the concentration of H3O plus from the acid base equilibrium. So, okay. So far we have been considering acid which is quite, whether it is the strength is low, or whether it is 100% dissociation and so on. We normally deal with not so strong acid. For example, HCl, even though it is 100% ionized, we call that a strong acid. But there are acids which are super strong, stronger than HCl, stronger than H2SO4 and so on. Okay, so how do we rate the acidity of this acid? So there is another indicator that we can use. They call it as Hammond indicators. Okay. If you want to read further on Hammond indicators, you can also go to internet and search for this part on the Bronsted-Lowry superacid and Hammond indicators. This is quite simply written and easy to understand. So you can see from here. For example, here you can see Bronsted-Lowry superacid and Hammond acidity function. Okay, so they call this as superacid. All right, superacid. So superacid is able to, for example, in this case, if we use HF as the catalyst for the reaction, so HF will be able to donate F to the sample that we want to use as in the reaction to form the product. It is super strong. So the ability to do that, is then now seen through the Hammett function, acidity function. Okay, let us see further on this one, right? That's why it is easier for me to use note because I can jump from one to another. If I use the PowerPoint, so I got to then go up from PowerPoint, then I got to gain share presentation and so on. They will take some time. Okay, so in concentrated acidic solution, Hammett and co-workers measured the tendency of acidic solution to protonate various neutral bases using Hammett indicators. Hammett indicators, right? For example, this is the protonated form. Protonated form of the nitroaniline. It forms para nitroanilinium ion. So this is the protonation occur, and the Ka value. Okay, after protonation, after the protonation process, so this has become an acid. This has become an acid, and it can catalyze another reaction. All right. So this the concentration of BH plus nitrolinium ion and B nitroaniline can be measured by spectrometric technique. Of course, if you in this case, if you want to do to see how much what is the concentration of para nitrolinium and also para nitroaniline, okay, so you just get the sample and put that into the UV visible. I'm not sure whether you have done any project. Probably some of you will start project and so on. Okay, so in UV visible we have A, right? We have the lambda, all right? So and then you have got the spectrum, right? So and then you can relate certain part to lambda max of certain species uh, in the reaction mixture. Okay. So for example, say this is for so you can say this is A, this is B. So this is then for A, for example, and this is for B, right? So and then you can take that as the value at certain concentration, right? And then you can relate to the concentration. You can plot graph, okay? I've seen, probably you have done this, and then this is what we call as the A versus concentration. Let's see. Okay, A value versus concentration, or the other way around, okay, can also. And then you can relate this to this, and then from there, if you know certain value of A, then you can then get the value of concentration, right? So this is called as calibration curve, and from there, you can get the concentration of A and B as the reaction go on, for example, or after the reaction finish. That is by spectrometric technique. What is spectrometric technique? Is when you use UV visible spectrophotometer, for example. So that is one of the way of analyzing the concentration of species in the reaction. So in this case, for example, you can straight away analyze both concentration, because if they both will give you a different lambda max, then it will be much easier. Okay, back to the Hammett acidity constant. Right, so the Ka for this reaction is known, okay, as this, okay. So I'm not sure whether you know about the activity. I think you have already learned activity, right, from your CHM 3101. Right, so you have, all of you have taken 3101. We know that activity A is equal to activity coefficients time the concentration. Okay. and the concentration. Okay, so the activity coefficient can take value from 0 to 1. Okay, so meaning that A, where I get this here? A is not necessarily C, right? Meaning that not all concentration that you expect to be contributing to the activity of the acid, for example, in this case. Okay, so it depends on the A value. On the A value. Okay, for this, so that's why the strength of acid from the activity of person that is contributed from the acid. The concentration of acid is contributed from the acid. Okay, so then that can be related to the Ka value of the acid. And the Ka value of the acid is given by this in terms of A. So we have seen in terms of concentration before, but to be more accurate, it should be in terms of A. Right. So then you can see here you have the AH plus, and then at the same time AB can be written as this, and then ABH plus as this, right? So it all involve the gamma, right? So where gamma is the activity coefficient for B and gamma B is the activity coefficient for B, and gamma BH plus is the activity coefficient for BH plus, right? And then we just leave AH plus there. By right, you can also change AH plus. AH plus is equal to H plus times the concentration of H plus. That should be the way. But we only interested in looking at the activity of H plus. We're not interested in looking at the concentration. So we then we just let the AH plus remain AH plus now, without changing it to the gamma H plus times the concentration vector H plus. So taking logs yields of this equation, so you have got this equation, right? So and then we define a new parameter H naught of the H0 or H0, and this is as we call this acidity, acidity function, and H naught is only taking this part, right? So the part which has the activity of H plus and also the activity coefficient of B and BH plus. So that is the acidity function, right? So you know now what is the Hammond acidity function, okay? And then the